The molar mass of NaOH is 40.0 grams of NaOH in 1 mole of NaOH. And then I'm given this enthalpy, which tells me that 1 mole of NaOH will release 44.51 kilojoules, which tells me that Q of the system is minus 55.6 kilojoules. So now I can move to Q of the surroundings. Q of the surroundings is going to be equal to the mass of the surroundings, which we're going to have to give ourselves a minute. Our mass of our surroundings is going to be 1 liter of water in 1 liter, there's 1,000 milliliters. And then in 1 milliliter, we have 1 gram of solution. And so this gives me 1,000 grams of surroundings. So I have 1,000 grams. My specific heat of water is 4.184 joules per gram degrees Celsius. And I'm looking for my final temperature. And my initial temperature is 20.0 degrees Celsius. Now, right now, as I'm looking at this, I have 2 unknowns, Q of the surroundings and TF. So this is where I need to use my first law of thermodynamics to help me out. And so I know that Q of the surroundings is equal to minus Q of the system. And so Q of the surroundings is equal to 55.6 kilojoules. Now, I'm looking ahead. We're going to run into a problem because in my heat capacity, I have joules, and here I have kilojoules. That's going to give me a problem. So I am going to look ahead, and I am going to convert to joules. Okay? So now I know that Q of the surroundings is 5.56 times 10 to the 4th joules is equal to 1,000 grams times 4.184 joules per gram degrees Celsius times the final temperature minus 20.0 degrees Celsius. And if I do my algebra, I find that the final temperature is going to be 33.3 degrees Celsius. Now, I'm not quite done because, well, I have an answer, but the next step is to sanity check this answer. So if I look back here, I have a negative sign on this delta H, which means that this is exothermic. So that tells me that my final temperature should be bigger than 20. And if I look back at my answer, that is what I get. And so therefore, I'm pretty confident that I have done my algebra correctly. Okay, so in the next video, I'm going to do another example Very similar to this one, but going at it from from a different direction and solving for a different piece. So if you're still struggling with these questions, stay tuned and there will be another video. Okay, so welcome back. Let's do another example of how we work with this molar enthalpy of dissolution. This enthalpy, really, if we say the word enthalpy, we're really talking about this delta H value. And we can have lots of terms, lots of descriptions trying to say what this is a delta H of, but in reality, all of this is really talking about an energy change of a system, and we are going to work to calculate it. And this example is looking at the molar enthalpy of dissolution for when we dissolve ammonium nitrate in water. And so what we have, if we define our system, we have ammonium nitrate, NH4NO3, and we are solid. And we are going to put this into water, and this is going to break apart and dissolve in its ions. And we want to know what is the delta H for this reaction. So in this case, it tells us that 3.88 grams of ammonium nitrate is dissolved in enough water to create 58 milliliters of solution. The density of solution was found to be 1.03 grams per milliliter, and the temperature of the water decreases from 23 to 18.4. So, as I'm thinking about this, I defined my system. I should also define my surroundings. In this case, the surroundings is going to be the water that is doing the dissolution. Now, the next thing that I should do is I should think about this information that's given to me. This water decreases in temperature. This should tell me that it should clue us in that the system is endothermic, because the system, this guy, the reaction that we're interested in is removing energy from the surroundings. And so this means that we expect the delta H to be bigger than 0, to be a positive number, indicating that this reaction is endothermic. Okay, so when I look at this problem, I take stock of what I'm working with. And I start taking track of what I know. And since I have this information of the temperature of the water decreases, this should tell me that this is what we are measuring. We are measuring the water, and that the water is our surroundings. And so this should clue me in that I should be able to find Q of the surroundings is going to be mass of the surroundings times the specific heat of the surroundings times the change in temperature of the surroundings. Now, to find the mass of the surroundings, I'm going to have to calculate that because I'm given a volume and a density. And so my mass of my surroundings is going to be equal to my 58 milliliters and I have 1 milliliter is 1.03 grams for my solution. And so my mass of my surroundings, if I do this math, becomes 60.0 grams. So I have 60.0 grams. The specific heat of my surroundings, we can assume we're working with water, basically, is going to be 4.184 joules per gram degree Celsius. And my temperature change is going to be T final is 18.4 degrees Celsius minus 23.0 degrees Celsius. And so Q of my surroundings, if I do this math, Q of the surroundings is negative 1,154.8 joules. Well, the question is not asking about surroundings. The question is asking about this molar enthalpy of dissolution. That is the system. And so now I'm going to have to use the first law of thermodynamics. And so this is where I can find that Q of the system is going to be equal to negative 1 times Q of my surroundings, or Q of my system is equal to positive 1154.8 joules. But I'm not quite there yet. I now have to convert this Q of the system to delta H. And our delta H of our system is going to be equal to Q of the system divided by the number of moles of our system. So this is where our 3.8, let's start with finding the moles of ammonium nitrate. So I have 3.88 grams. The molar mass of ammonium nitrate is 80.022 grams per mole, which means that .0485 moles of ammonium nitrate reacted. So now I can find delta H of my system as 1154.8 joules divided by the moles. And I can find that delta H is equal to 23,810.3 joules per mole. Or if I want to put this in kilojoules, I get 23.8 kilojoules per mole. Okay, so you should notice with these problems that really I am working these problems in 3 steps. I am finding one of the Q's, and depending upon the information given, this could either be Q of the system or Q of the surroundings. In this example, it was Q of the surroundings. After I have one of the Q's, I use the first law of thermodynamics to be able to find the other Q. And then I use that information to answer the question. So remember that this delta H really is the energy flow in the form of heat. It's just that we are accounting for how much substance we are using. So in my lecture, I talked about how the amount of heat that we get from a fire when we put one log on the fire is different than the amount of heat we get when we put 2 logs. In order to make this sort of a constant number, we make this per mole so that we know how much is involved in the reaction that we are talking about or in the system that we're talking about. And so in the case of the fire, we could take the amount of heat divided by the number of logs, and we could get an enthalpy in energy per log. Okay, I hope this starts to help a little bit. I know that you've seen other ways of doing this. I'm hoping to give you these examples so that you have a consistent reference source of how we go about solving these problems in the textbook and in your homework and on your exams. Remember, Dr. Chamberlain and I have lots of office hours. We answer emails. We are here to help.